Hi, so today I want to talk about the 87-86 strontium isotope ratio evolution of the oceans. And so first of all, let's take a look at what that looks like. So here is a plot, 87-86 ratio versus age. And you can see there's a curve here. It goes up and down, up and down, up and down. Where do these numbers come from? They come from marine carbonates. Carbonates have very high strontium concentrations, very low rubidium concentrations, so they record the isotope composition of the oceans at the time the carbonates form. Now, to remind you how this works, 87 rubidium is radioactive, and it decays to form 87 strontium with a half-life of about 48 billion years. The decay constant for that, lambda, is about 1.4 times 10 to the minus 11 per year. Okay, so what is it that drives this variation? Well, there's two end members that we can think about. One of them is mid-ocean ridge basalts. And those basically represent the isotope composition of the mantle. And these have varied from about 0.699 at the creation of the Earth 4.5 billion years ago, up to present day values that are around 0.702, 0.703, around there. So if we go back to this diagram, we see that the minimum values here are not as low as more. More would be down here somewhere. And so we can see that we're seeing more of a mantle signature as we go to lower 87-86 ratios. We're seeing something else as we go to higher 87-86 ratios. Now, what is it that creates those higher 87-86 ratios? That's continental crust. It's not just any continental crust, it's old continental crust. But what are the values that we might predict for that? Well, to sort this out, we can look at radioactive decay of rubidium to strontium, think about what the concentrations might be in continental crust, and calculate the range of strontium isotope compositions that continental crust might be contributing to the marine system. Okay, so let's just take 2 billion year old continental crust. And then what's the rubidium 87-86 ratio? I looked this up from a compilation of continental crust compositions from Rudnick and Gall, and they suggest that a common 87 rubidium, 86 strontium isotope ratio might be on the order of 0.5. It can be higher than that. There's certainly granites that have values that are 2, 3, 4, or even higher in some cases. But let's just take average continental crust and see where that gets us. Okay, so from the decay equation, we can write 87-86 is equal to an initial ratio. We could take Morb as an initial ratio. That'd be the lowest that it could possibly be. Something on the order of 0.7. Okay, so let's set that to 0.70, right? Plus 87 rubidium, 86 strontium, right? Which is going to be 0.5. And then we have e to the lambda t minus 1. So lambda 1.4 times 10 to the minus 11. 2 times 10 to the 9th minus 1, right? What is this equal to? Well, if you multiply this out, you get 0.028, right? And this is a small number. So we're going to play a little trick here. We're going to expand the exponential as a Taylor series, okay? So now this is going to be equal to 0.7 plus 0.5 times The Taylor series on an exponential of a small number is going to be 1 plus 0.028 plus 0.028 squared over 2 factorial. We're not going to carry out the other terms. You can see these are getting pretty small, and so those numbers are not going to matter. And then we subtract off 1. Right? So these terms are going to cancel out. These terms, we're just going to ignore them because they're too small. And so this becomes 0.7 plus 0.5 times 0.028 is 0.014, right? And so that's going to be equal to 0.714. That's average continental crust 2 billion years old. So if we go back to our plot and look at the values, the minimum values are not as low as Morb. The maximum values are not as high as average continental crust. And like I said, there are plutons that have much, much higher 87-86 ratios to them. And so what we're looking at with this figure then is a variation in the contribution of Morb to the isotope composition of the oceans versus older continental crust in contributing to the isotope composition of the oceans. Now, what is going on here? Why does it go up and down? It's been proposed that these variations represent varying contributions from weathering of origins. So if we look at the tectonic orogeny is the collision of a primitive arc against North America. Well, a primitive arc is going to have an isotope composition that looks more like Morb, and so when we weather that material, it's going to draw the 87-86 ratio down. The Caledonian is a collision that involves the ancient craton of Europe. The Indo-Asian collision over here involves ancient crust from India. So these have very high 87-86 ratios, and as they get weathered, they increase the 87-86 ratio of the oceans. And so the up and down variation is telling you something about contributions of old continental crust at the high end versus primitive Morb-like compositions at the low end. All right, thanks very much.